introduction, we start this for this course. We start with the introduction, and in this we will discuss here the basic concepts that are commonly used in analysis of fluid flow. I will invite your attention to the two words, basic concepts. So here in this discussion, we will be discussing mainly focusing on the basic concept. They are very essential because for whatever equations, whatever problems, whatever situation we shall be discussing, formulating equations and so on, the utilization of these concepts is very important. And therefore, initially it's better to introduce some of the things that are necessary to set the stage for the course. So therefore, we will discuss some of the basic concepts that are needed for analysis of the fluid flow. When we finish discussing this section, one should be able to understand the basic concepts of fluid flow problems and solve them. So understanding the problem and then solve them, because this is a course of applied mathematics, as you know, and it's applied, it has applications. So therefore, one needs to understand it, correlate it with mathematical equations and be able to solve it. Also understanding the basic concepts of fluid mechanics. Now this is different from what I said earlier. That was for fluid flow problems. This is fluid mechanics. And then recognize various types of fluid flow problems encountered in practice. So we will appreciate different types of problems that we face, and we will be discussing them as they come, and you will know, and we should be able to differentiate them, one problem from the other, and how to decipher them. This is very important, what conditions to apply on them and so on. So for that we should know the physics that goes behind it. Model the engineering problems and solve them in a systematic manner. Modeling a problem is a difficult part. So therefore, if you have modeled a problem in a proper manner, you should be able to provide a good solution for it. Having a working knowledge of accuracy, precision, and significant digits, and recognize the importance of dimensional homogeneity in engineering and our calculations. You see, it's very important. You will know that there are a large number of things in which there is a little bit of tolerance level, there is a flexibility, but there are things that need precision, accuracy, extremely important things. And just for sake of discussion, I may say that in our daily life, unfortunately, at many places you will see that we are not very particular about precision. For example, if I have committed to be there at 11, if I may reach at 11:15, I think I have made no mistake and I ignore it. This is not on. When it comes to engineering problems, they have to be very precise, otherwise things will fail. I will give you many examples in this regard where failure in precision, failure in estimation and accuracy can result in disasters, and where if you have put the things correctly, then you achieve success. So therefore, all these things are extremely important in fluid mechanics, in the case of a problem that we'll be dealing with fluid mechanics. We discussed the basic concepts such as the numerous ways of classification of fluid flow. Fluid flow can be classified in a number of ways, and we shall be doing that soon. Such as, to give you an example, viscous flow versus inviscid regions of flow. So viscosity and where there is no viscosity matters. Internal versus external flow, compressible versus incompressible flow, laminar versus turbulent flow, natural versus forced flow, steady versus unsteady flow. So all these are different types of flows, different categories, and we need to deal with them accordingly. We also discuss the no-slip condition at solid-fluid interfaces and run through a brief history of development of fluid mechanics. Concepts of system and control volume, etc. will also be discussed. So as I have mentioned, these things are very important, and we need to appreciate these differences, these categories that I have mentioned. Mechanics is the oldest physical science that deals with both stationary and moving bodies under the influence of forces. So one of the oldest subjects, and many people have contributed to its development, and the mankind has been observing this phenomena for long time. The branch of mechanics that deals with bodies at rest is called statics, while the branch that deals with bodies in motion is called dynamics. So I am sure you are familiar with these things even in rigid body mechanics. Fluid mechanics is defined as the science that deals with the behavior of fluids at rest, we call it statics, or in motion with fluid dynamics, and the interaction of fluids with solids or solid fluids at the boundaries. Fluid mechanics is also referred to as fluid dynamics, and in most places we like to call it as fluid dynamics, that's because that is more interesting, by considering fluids at rest as a special case of motion with zero velocity. The study of the motion of fluids that are practically incompressible, such as liquids, especially water and gases at low speeds, is usually referred to as hydrodynamics. Gas dynamics deals with the flow of fluids that undergo significant density changes, such as the flow of gases through nozzles at high speed. The category aerodynamics, it deals with the flow of gases, especially air over bodies, such as aircraft, rockets, and automobiles at high or low speeds. You may know already that the things like aircraft, they largely depend upon the air movement as well, the exhaust, because they provide the thrust and the lift with which the aircraft takes off. Similarly, this flow of air over the bodies like cars, automobiles, or other vehicles, they are very important. They are affected by the speed of air that flows over them because it creates drag and so on. So therefore, all these things are put together, are considered under aerodynamics, and which is in itself an important branch of fluid dynamics. So we shall be considering some of the things later on in detail.